So I've had just an overview of the proof so that you have an idea of where this is going. But now let's see the proof with all the details. So again, how does the proof work? We start defining this subspace, right? For each k, that will be the range of n to the k. So it starts being the whole space. Okay? It starts being the whole space. And as we apply n to it, again and again and again, you're just losing dimensions. You're just shrinking and getting smaller and smaller until at some point you're just this point here, which is the vector, the trivial vector space. And that will happen at some point before n, typically. Okay? But we start from there and we keep going backwards. We start for there, empty set is a basis, is a trivial basis for this trivial vector space. So all we have to do is, starting from a Jordan basis to the space uk plus 1, how do you go down from k plus 1 to k? So from having a basis bk plus 1 for uk plus 1, which is a subspace of uk, we're going to construct a basis bk that works for uk. That's the strategy, and that's what we're going to do. And if we can show this step, then by backwards induction, we can just go down, 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 until in the end we have a Jordan basis b0 for the space u0. But, well, what is u0? u0 is just v, so we're finished. So our work will be how to go from bk plus 1 to bk. So let's show this. Suppose we have a Jordan basis, and we know Jordan basis always has this form. It is a vector, then n applied to this vector, then n applied to the other vector, then n applied, and so on, until at some point you get a basis that if you don't apply n anymore, but you know if you did, you would get 0. And you have a few blocks like this, and then it goes to 0. Maybe the block is so short that it only has v and nothing else, and you apply, and v is an eigenvector. That's a very short block, it's also allowed. So suppose we have a basis like this, and, well, note that uk plus 1, what's uk plus 1? uk plus 1 is the range of nk plus 1, which we can think of as the range of n on the space uk. Because to arrive in uk, you need to apply n k times anyway. So when you apply n again, you're necessarily in uk plus 1. So I'll let you think about it for a while. Okay? If it's not clear, stop now and think about it. uk plus 1 is nothing but the range of the operator n if we take the restriction of the operator n to the subspace uk, where uk is the range n to the k. Okay? Can we continue? Let's continue. So, we know since uk plus 1 is the range of n restricted to uk, we know there exists u1, u2, un, such that if you apply n to these vectors, you get these vectors. So what we're doing here is we're adding more vectors at the beginning of these threads, at the beginning of these chains, thread. So we define these vectors by solving these equations. The solution in general is not unique, it does not matter, just pick one. So we insert these vectors at the beginning of the chain, so the chains, they got larger. And we got a new basis. I'm not calling this basis bk, because maybe it's not bk. Maybe it doesn't have many vectors to span the entire space uk, where we are working here on uk. Okay. So the point right now is if we append this, if we insert this vector here, and then this vector here, just before the original chain, then the new chain we get is linearly independent. So maybe it doesn't span the whole space, but at least it's linearly independent, so we can, later on, we'll extend it to get a basis. How do we show it's linearly independent? That's similar to a trick that we did in class. So how do we show they're linearly independent? We let alpha be a collection of scalars such that this equation, this linear combination gives 0. What we have to show here, we have to show that all the scalars have to be 0. How do we show that? Well, we just apply n to the equation. When we apply n to the equation, this u becomes v. And this v1 becomes n v1, and this one goes to 0. So the last one disappears. The last one disappears. And now all what we have is here v1, vm, and here n v1, etc. So we're back with the same bases we had before, just the coefficients have been shifted. Okay? And now we know that the basis we had before was linearly independent. Yeah? So let me write this here. So this u1 became v1, um became vm. And this one here, it became 0. Okay? This one here became 0. So if we discard the ones which became 0, we get a collection of vectors which we knew already was linearly independent. So this gives us that these alphas are all 0. Are you sure? All of them are 0? Oh, not yet. Yeah? These ones we don't know anything about them, because these, the last vector in the chain, when we applied n to the equation, they disappeared. They vanished, because these vectors, they go to 0 when we apply n to them. Okay, so these ones we don't know yet that they are 0. But now every other vector is 0. Every other coefficient is 0. So the previous equation, if we look at it, it became much shorter. And now these, now we see they have to be 0, because these are linearly independent. So it has to be 0. So we use linear independence twice. That's a trick that is the key in this proof here. So also the last coefficients, which is this one here and this one here, they are, no, this one here and this one here, they are all 0. This proves the claim that they are linearly independent. So now let's continue in the last video of how do you extend, if necessary, this linearly independent family to get really a basis for UK, but not just any basis, a Jordan basis.